Hello, everyone.
Hello, Professor. How you doing?
All right. All right, we'll wait. Let's see how many people have we got here. 11 people. We'll wait a couple more minutes. While we're waiting, next Wednesday, the Optical Society of Southern California is having its February meeting, and the speaker is going to be Nader and Geta. Who I think is now at UT Austin, but he's a big guy in the field of metamaterials, materials that have a refractive index n less than 0. These materials are still considered fairly exotic. They're not things we discuss in this class because for now they're still quite specialized materials. That won't always be the case. I think someday metamaterials will be used much more widely. But it's a very fascinating thing, the topic of metamaterials and how a refractive index that's negative means that you get, well, sometimes negative refraction. If you've got N1 greater than 0, N2 less than 0, you get a wave traveling like that. So Snell's law still works. It's just that theta 2 becomes negative, and so it gets deflected in the opposite direction that you would have predicted. And besides having certain practical applications in terms of deflecting light in different ways, it turns out to enable people to get around the diffraction limit, at least in principle, so they can potentially see things smaller than the wavelength of light. And so if you want to go to this online seminar, just go to ossc.org and sign up for the talk. Any questions? I know that they're trying to increase opportunities for networking at OSSC meetings. They're going to try to do some things to get more interaction rather than just logging in and listening to a seminar. And given that many of our alumni have found their first job through going to OSSC meetings, I know it's not the same going to a Zoom or WebEx OSSC meeting, but still, I would strongly recommend learning about the organization, and then I think there's a good chance we'll be in person. Well, I think OSSC meetings will be in person this fall because ironically, the OSSC membership does skew a little old, which ironically means they'll be the first to get back to normal because they're all getting vaccinated first. The other thing I'll say, did you guys get an email from the administration about in-person classes in the fall? Did anyone see?
Yeah, I did.
What did they say?
It was basically, are you just talking about how the email was like, we plan to have classes in the fall from Cal Poly? Or you just
Sure. I don't know how many emails you got from them about fall, but what did they say?
They're just like, yeah, we're still planning on having classes in the fall due to the uprising, vaccination, stuff like that. I'm trying to find the email, but it wasn't anything specific. They were just like, we're planning on it.
Okay, well, I'll tell you that we're planning to offer, okay, I see a message, you won't get confirmation of class schedules until March. Yeah, the reason is that those of us who do class schedules were kind of kept in suspense about what the plans would be. And they just told us a few days ago that they plan to allow a limited, more in-person classes than they had this semester. Lab classes will be well, some lab classes will be in person. In our department, all of the sophomore, junior, and senior labs will be in person, but the intro labs will still be online simply because they want to run the classes at reduced capacity, fewer people in the room. Small lecture classes will be in person. So math methods with 50 or 60 people won't be in person, but the recitation sections where you got 20-something people doing activities, those will be in person. All right, at this point, we've got most of the students. So let's get started. Last class, we spent a lot of time using the thin lens equation. And we learned that 1 over S1 plus 1 over S2 is 1 over the focal length, which is the refractive index of glass minus 1 over R1, the radius of the left side, radius of curvature of the left side, plus the refractive index of glass minus 1 over negative R2, the radius of curvature of the right side. And you practiced to some extent with that thin lens equation. Now what I want to do is I want to design a lens with a refractive index, with a focal length f equals 10 centimeters. And let's say that NG is 1.53. That's BK7, a very popular glass used in many optical components historically. And there are many combinations of R1 and R2 that would give you this focal length. But let's say that minus R2 equals R1, which just means it has the same curvature on both sides. That's all. Then my question to you is, what should these radii of curvature be? How do we figure that out?
The thin lens equation?
Yeah, we use the thin lens equation. More specifically, what would we do?
Well, actually, so we take the difference of the index of refraction from air and put that, sorry, we're looking for radius
Radii
of
of
curvature.
curvature.
Yeah, like that. So then you'd have to flip it.
Because I replaced minus R2 with R1. So that's 1
Yeah,
over R1.
that'll give you a factor of 2.
All right, so R1 should be 10.6 centimeters. So let's try that. Let's just design a lens from scratch in Zmax. Turn on Zmax. I'm going to switch screens. All right, and let's just do this completely from scratch. Now let's think, we're going to have the object surface, right? We're going to have a surface with an object. Then we're going to have something to the right of it. Then we're going to have a glass surface, then another glass surface, and then the surface between, so we're going to have the surface between the object and the first glass, the glass layer between the two surfaces, and then we're going to have the space between the lens and the image. Oh, and let's say we want to have the same distance from the object to lens and the lens to the object. So how thick would we make that first layer? Let's actually do one more thing with paper and pencil. Let's say we want S1 equals S2. Let's see here, 1 over S1 plus 1 over S2 is 1 over 10 centimeters. So it's going to be 1 over S1 plus 1 over S1, since S1 and S2 are the same. That's 2 over S1. So S1 is going to be 20 centimeters, it looks like to me. So then I'm going to go back in to Zmax. Let's check our units. Okay, then we're going to make something, I don't know, this lens might be about 1 centimeter thick. It's going to be made out of BK7. And we're going to have to, right away it has the image surface. We don't want that. So we're going to have to insert another surface here. And we already worked out what the radii of curvature should be. We got 10.6 and minus 10.6. And what should this layer thickness be?
Sorry, what was the goal for that layer?
Well, we wanted to have, what was the goal for that layer? That's the layer that's between the object and the image. And I said that we're going to design for a focal length of about 10. And we want the same object lens and lens image distances.
It should just be the same as the other layer, right? One for the thickness.
1? Oh,
20.
Sorry.
What?
Should be 20, right?
Yeah, it should be 20. 1 is the thickness of the glass. So let's go and make a cross section. And I don't see anything. So let's see here. Any ideas what might be wrong here?
Don't we need the semi-diameter?
Yep.
The clear semi-diameter?
Yep, the semi-diameters are both 0. All right, so we make the mechanical semi-diameters 2, and we better make the clear semi-diameters 2. Okay, that helps. But we still have this problem that the bundle of rays is not, has 0 thickness. So what are we going to change there?
Aperture?
Yep. Aperture pupil diameter. And right now, surface 1 is the aperture stop. So let's make that diameter, well, the semi-diameter is 4. So the full diameter, the semi-diameter is 2, so the full diameter is 4. I'll make it like 3.9. Okay. This seems to more or less work. Any comments or questions so far?
Could you actually quickly go over the difference between clear and mechanical semi-diameters? I mean, I kind of get it visually, but I just want to make sure.
So mechanical semi-diameter is just how big this is, how big the physical piece is. The clear semi-diameter is how big is the region that's transparent. It could be that even though mechanically this thing has a semi-diameter of 2 centimeters, maybe part of it is blocked off by various attachments, things used to hold it in place or whatever.
Oh, okay, thank you.
So if we change the clear semi-diameter to 1, then what happens is that light hits it, but doesn't go through. And there are all sorts of reasons why you might put something there. Anything from, we simply don't want as much light, so we put some sort of something dark on there to block and absorb light. Or maybe in order to hold the lens in place, you've got something there. There's any number of reasons why the clear semi-diameter may be different from the mechanical semi-diameter.
So that's basically the way you'd, I guess, adjust the aperture for different layers, since the
That's one way.
aperture setting is it only applied to the first?
We could adjust it. We could always make a different layer the aperture. When we say the entrance pupil diameter and the aperture stop plane, besides blocking rays by explicitly changing the transparency of this piece by putting something on there, somebody could always just put an iris in there. An iris is just a circular opening that can either be completely closed or completely open or anything in between. We can always put some sort of iris there to partially stop it. And so what we're saying is when we specify the entrance pupil diameter, we're saying how wide do we want this bundle of rays to be at whatever surface is functioning as the stop. So if I were to say go to surface 2, I could always change surface 2 to become the aperture stop. And we're not going to notice much of a difference here because the rays are basically going parallel to the axis. But let's make their trajectories inside the lens a little more dramatic. I'm going to make this layer thickness 15, all right? So that there's a little more of that. And I'm going to make these mechanical semi-diameters larger. And I don't want to have to keep on editing. So I'm going to pick up from the previous surface, from surface 1. All right. And I'm just going to do the same here. I'm going to pick up from surface 1. I'm going to make this 3. All right. And when we do that, we'll get to the whole edge of the lens thing in a little bit. But I'm just going to pick up from that. And by making it a little bit wider, we can make somewhat more dramatic deflections of the rays. What I'm trying to do is I'm trying to get the rays to go up more. All right, I'm trying to get the rays to go up and it's not really working. I'm gonna have to widen this more. I want the rays to make more vertical trajectories. So instead what I'm going to do is I'm going to make this infinity. I don't see why that is an issue. Whatever, I have no idea why that. Okay, I wanted the rays to go up. Instead of making it, I should make it minus 5.3. Okay, what I want is I want some upward deflection of those rays. And you'll see why. We're going to zoom back out. And if I get upward deflection of those rays, I'm going to then focus this. How do I focus this?
Optimize.
Yep, we go to optimize, quick focus. All right, and that is frankly a terrible focus. This is a terrible lens design. It has way too many aberrations. But we're going to analyze the spot diagram. So we're going to go to a standard spot diagram. And that's what we've got. And it's hideous. But, you know, we're just illustrating a point here. Now, if I make the aperture 5 and this surface is the stop, that means that everything that hits the edge, the outermost edge, is 2.5 centimeters off axis. And you're saying, well, I don't see 2.5. I'm going to sample with a higher density of rays. All right, so this topmost is getting more towards 2.5, all right? Well, if I, okay, so we've got that, and we just lost our spot diagram. Let's tile all windows. Okay, I'm going to change this now. We're going to keep it at a width of 5. But you see, before it's a width of 5 here. And we know it comes up a little bit between the left surface and the right surface. Okay? And so we're saying that the width has to be 5 on this surface. Now I'm going to change it. Make surface 1 stop. And this thing changed a little bit. You probably weren't looking at the spot diagram and the distribution of rays in the image plane, but let's just take note that it's RMS radius. Anybody want to guess what the RMS radius of this thing means?
I mean, besides what RMS means?
What is RMS?
Root means square?
Correct. So radius, each of these rays is coming in at a different distance from the center. It's just calculating the root mean square, or the square root of the average square distance from the center. Some people might not have heard RMS. So imagine it, instead of averaging the distance from the center, you average the squared distance and then take the square root. And people do RMS averages because sometimes you're averaging positive and negative, left and right. And so they do an RMS average, squaring everything to get to the average of the square distance, so we don't have to worry about negative things canceling out. All right, so right now the RMS is 3,504 microns. And make this other surface the stop, and it becomes smaller. Okay, so we actually get better focusing in the case where this surface is the stop, because if the right surface is the stop, that means that the width is 5 centimeters here. It's narrower than 5 centimeters there. Whereas if the other surface is the stop, it's 5 centimeters here, it's even wider there. So we've widened the beam, and widening the beam tends to make the spot sizes bigger. We don't get as good focusing. I've tossed a lot at you. Someone asked me a question. Anybody has a question?
This might be an obvious answer, but I was just curious that pattern that's formed, right? Those spots are basically the wave fronts from the diffraction pattern from the lenses and the aberrations.
No diffraction here.
Oh.
These calculations don't include any diffraction. This is just, they send a whole bunch of rays through, kind of like here, and then they see what happens, okay? And we could always change the ray density, and as we change the ray density, that will change. Now, what happened was that I did a different case. Let's go back to this nicely focused case where we had the biconvex lens. So we've got the biconvex lens. It's convex on both sides. I'm going to turn down the ray density because you can't see anything. I usually stick with 7 rays. That's a good number. All right. So we've got our biconvex lens. And let's get everything focused again. All right. You should notice that when things are well in focus, the patterns tend to look like this, meaning pretty well clustered in the middle and then fanning out farther on the edges. When you're way out of focus, I can move this way out of focus. It tends to look more like that. It looks closer to uniform. So I could just look at a spot diagram and tell whether it's in or out of focus. Like I look at the spot diagram and it looks pretty good, but I know that if I do a quick focus, it will get a little bit different. And I can just kind of tell sort of by now. This one just doesn't look right to me. Other questions? Well, let's just verify a few other things. Let's verify that it qualitatively obeys the thin lens equation. We saw that if we moved the object in closer, the image got farther. And yeah, you see how when it's really, really, really out of focus like that, it almost looks like a bulging globe. So we saw that if it's really out of focus, sorry, if you move the object in closer, the image goes out further, and vice versa.
I have a question.
Yeah.
Could you somehow like quantitatively show how well focused an object is using like vector analysis of these diagrams?
Using the what analysis?
Like vector analysis?
That's basically what we're doing with the RMS radius. We're basically just calculating the spot size. And when it's in focus, then we have minimized the spot size. So like here's, right now this is in focus, minimize the spot size. If I went to 15.1, this is slightly away. Notice that right now the RMS radius is 569 microns. It goes up to 596. I move it farther out, it goes up to 655. And it's just going to keep on increasing.
Right here? Right here?
Right. So as we change the, as we move, we are going to see, as we move the image plane, we're going to see that the size of the spot diagram changes. That's how we quantify the focus.
Okay, so it's the smaller size means we have a well-focused object, correct?
Yeah.
So then like those like sort of outlying concentric pieces, like the farther they are, they kind of contribute less.
No, they contribute more because when you compute an RMS,
Oh, yeah. Sorry. Yeah, I understand.
now there are other kinds of spot diagrams that we could do. That's called a standard spot diagram. Let's do a through focus spot diagram. All right, and a through focus, I'm going to tile all windows so that we can see the through focus. Actually, window options, I think I'm just gonna dock all windows. Here's what a through focus spot diagram is. A through focus spot diagram sees how much it changes as we move in and out of focus. Here's the case with the minimum spot size. And we can see that if we move 50 microns in either direction, we don't change things that much. That's good, that's robust, all right? If you can move your image plane, move your detector left or right a little bit and still get a pretty sharp image, that means that your alignment isn't too finicky. Whereas if you have a case where moving your image plane ever so slightly would take everything completely out of focus, well, that's bad. You have a very finicky alignment. Any questions?
So the more dots that you have like closer to the center means it's just like closer to the focal point?
Well, the standard the standard thing that Zmax does is they don't do completely uniform sampling. They use something called, you can use a square, hexapolar, or dithered arrangement. There are different ways of sampling. So what you're seeing is not that they started with a completely uniform distribution and then some of them got sent away from the center. They tend to do a lot of sampling slightly off center. So it's a product of two things, the way that they sample and the way that the lens performs. Other questions?
What does the other radius on the bottom refer to?
Georadius,
Yeah.
I believe that is just the actual outermost radius. Geometric. Let's see here. Okay, well, we can just look at it in terms of scale bar. This is 2,000 microns from top to bottom. So going 974 microns out, it's 2000 micron radius. So it's 1,000 microns from here to here. 974 out is almost the entire way. And we see that these topmost dots are pretty much at the edge. So it's just the geometrical radius of this entire pattern.
Is there a particular reason why you'd want to pay attention to that in addition to the RMS radius?
Usually not, but somebody somewhere wants it, so they put it on there by default. Other questions? Let's go back to this layout. We can add more fields. So let's add a field. We'll put it off axis by, now we gotta be a little bit careful. Let's see how we're quantifying fields. Right now it's quantifying fields by angle off axis. Let's change it to object height. Let's put it 1 centimeter off axis. Now, this was, I believe, focused before. I just want to double check the lens data sheet. Yeah, that was focused. Watch what happens to the lens data sheet when I focus it again. Do you see how that layer thickness changed ever so slightly? It's not a huge change, but you might ask, well, why would it change at all when I add a second field? Anyone care to guess?
Just trying to focus it on the off-axis field as well.
It's trying to balance between the off-axis and on-axis, because right now they're both given equal weight. All right. If I give it the same number for both weights, then it tries to strike a compromise between the two. If I were to say make one of these weights 0 and the other weight 1, then we'd only worry about the 1. If I made one of these weights 1 and the other 0.5, it would give more priority to the 1, but some priority to the 0.5. All right, and so it gives you the option. Sometimes people care about everything in their field of view. Sometimes they only care about the center of the field of view. Other questions? All right, so at this point, we've got something that qualitatively does what the thin lens equation says. We know that it turns out to be more than just qualitative. But so far, all we've really shown is that it's qualitatively consistent with the thin lens equation. Object close to the lens, image far away. Object far from the lens, image close in. Your next assignment is to test the thin lens equation quantitatively. Now, there are a few ways that you could test it quantitatively. You could try to fit the thin lens equation to it. We know that 1 over S1 plus 1 over S2 is 1 over F. So 1 over S2 is 1 over F minus 1 over S1. So S2 is 1 over all that mess. I multiply top and bottom by S1F. That was not what I intended. I multiply top and bottom by S1F, I get S1F over S1 minus F, which winds up looking something like, if I just plot S2 versus S1, it winds up being a hyperbola like that. Approaches F as S1 is big, it approaches infinity as S1 goes 2f. All right, you could try to do that. You could absolutely try to do that. It's kind of a mess, and data analysis is always cleaner if we do line fitting. So what I have posted on Blackboard is an activity in trying to get a line fit out of thin lens equation. If you look under files used during class, then you will see an activity for today. And it's based on something that you should have seen in I said physics 132 of 1510, I meant physics 132 or 1510. So I want you to take a few minutes to work on this. I'm not going to collect or grade this. I know I put points on there because at some point I was grading it, but I'm not going to grade it this year. I just want you to take a few minutes to work on it in groups. I will break you up into rooms and let you work on it. And I'll be coming through to check on things. Joshua, are you going to join a breakout room? All right, Juan, you need a breakout room. I'm going to put you in room 3.
Yeah, thank you. I don't know why, but I keep getting like logged out of Zoom. So like this whole class period, I'm like having to leave and join back. So I'm sorry about that.
It's okay. How's it going in here?
Kind of just getting started.
All right. Wait, you're seeing this under projects?
Yeah.
Okay, whoever saw it under projects, could you share your screen?
Is this not the one you're showing? Yeah.
Whatnot.
Uh, sorry, below the screen.
Aren't we doing the one on
Oh, that's what you're going to do for Tuesday. But what we're doing right
You
now,
want us to do that? Oh, okay.
I want you to do that before Tuesday. But what I want you to do right now is an activity on the thin lens equation graphs to help make sense of the thing you have to finish by Tuesday.
So where do I find that?
Go back to the beginning of this page, of the class page. On the left, go to lecture notes, files used during class, Thursday, February 4th.
Okay.
Ooh.
Wait.
And I want you, it's an activity to show you how to.
Oh, they look very similar.
Yeah.
Okay. I feel better now because they have this. It's just because they have the same equation initially. Okay.
Yeah, okay.
Interesting. Cool. Okay, thank you.
Mhm. All right. The other group had a problem with this. Are you guys looking at the activity under lecture notes, or are you looking at Tuesday's project?
Oh, I was under lecture notes.
Okay, good. The other group was looking at the project.
Got
yeah,
it.
lecture notes?
All right, how's it going?
Good. So far. Not that I can think of right now.
Okay.
Yeah, I'm just playing with it.
Any questions in here? What?
I don't think so. Sorry.
Okay. Anything I can help with in here?
I'm good right now. Thank you.
Yeah, I think we're fine. We're just some of us are on C, I think.
Okay.
Yeah.
one side.
I just solved for t squared, and then I wrote it as a linear function. So in the form mx plus b.
Oh, I see. Oh, okay, okay.
Yeah, and then I found the slope, and then I found the y-intercept from that function. Or sorry, from
Okay,
that
yeah.
form. Yeah,
That makes more sense. Yeah, because I tried moving everything over.
gotcha.
Are you still working on it, or are you done and waiting?
I'm still working on it.
Okay. What about everyone else?
I'm still working on it.
Okay. Any questions?
No, not as of now.
By the
I
way,
just,
do you have two logins? It's showing.
yes, I was just about to tell you, I opened up my Windows laptop and it signed me out of this one. So I thought I was out of the Zoom call, and now I'm just going to close out this Zoom meeting on my Windows.
Okay.
Yeah.
All right, I'll give everybody a few more minutes.
Thanks for checking.
How's it going in here?
Good. It looks like we finished C and we're working on D right now. How to
Okay.
I think you have an answer for D, but I'm not sure if it makes sense. Is the intercept 0?
No.
No? Okay, no, this equation's wrong then.
You would just find whatever y-intercept you get on that graph and divide that by the slope.
You divide the y-intercept by slope?
Yeah. So I plugged in so for the MS, I ended up getting k times the y-intercept divided by 4 pi squared, but my k is 4 pi squared over the slope, so the 4 pi squares canceled out. And end up
So
getting the
what you get t squared is 4 pi squared over k times m.
Yes.
So 4 pi squared over k is the slope of that graph.
Correct.
4 pi squared ms over k is the y-intercept.
4 pi squared over k times ms, yes.
Yeah.
Yeah. So after the algebra, a lot of things canceled out. The 4 pi squares ended up canceling out. And I got y-intercept divided by the slope for ms.
Okay. Oh, gotcha. Gotcha. I see what you're doing now. All right. Yeah, that's right.
That was very interesting.
Yeah.
Sure. For part D, I got the slope should be -1, and your y-intercept should be 1 over f, as long as we have the y-axis 1 over s1 and the x-axis as 1 over s2.
That is correct. All right.
Oh, we're back.
All right, now that everybody's back, here's what you should have found. I first wanted you to go through the kind of data analysis exercise you did in a lab a few semesters ago. And then you should be able to see how we would take this equation and turn it into something linear. We would just say that 1 over S2 is minus 1 times 1 over S1 plus 1 over F. So if we do this correctly, we put 1 over S1 on one axis, 1 over S2 on the other, then we should be able to fit a line. And if we did all of this correctly, what's the slope?
-1.
Slope should be -1, and the intercept should be 1 over F. And that's how you're going to do this project. You're just going to basically set up a Zmax file and do a few different S1 values. Each time you put in an S1 value, you just change the layer thickness, do a quick focus, see what S2 is. Change the layer thickness, do a quick focus, see what S2 is. And you're just going to do that over and over again. So there'll just be a matter of changing this number to something else, do a quick focus, and get another S2. And you'll do that over and over again. And then you'll say, okay, I've done that I've got a bunch of S1 and S2 values for one lens configuration and an on-axis object. Then you'll change your aperture and you'll redo it. Then you'll change where your object is. You'll change what the object height is and you'll redo it. Then you'll say, you know what, I'm going to change the configuration of this system. So instead of having the same radius of curvature on both sides, I'm going to make one of them flat and the other one more curved. And again, you'll just type in a layer thickness and do a quick focus. And type in another layer thickness and do a quick focus. And in all of these cases, you're not going to get the exact same numbers every time, but in all of these cases, you should get a slope that's pretty close to -1 and a focal length that is pretty much the same as in the other cases. So let's talk about why I'm having you do this. I mean, I fully expect Zmax to say that these simple lens designs more or less obey the thin lens equation. But one, they won't perfectly obey the thin lens equation. You should see that the thin lens equation is only approximately valid. And two, it's basically a test and calibration. Yes, we know practically that Zmax works, but in general, whenever you get a new toy, you always test it. Whenever you get some new software, you always feed it test cases. Not because you necessarily think the software might be broken, although sometimes software has bugs, but to make sure that you know how the software works. If you can feed in input that should give a simple and predictable result, and the software spits out that simple and predictable result, then you probably understand the software reasonably well, and the software probably works reasonably well. Failure to do simple calibration runs can be catastrophic. About 20 years ago, I went to a seminar by a physicist who was doing high precision tests of Newton's law of gravitation, just checking the inverse square law of gravity. And he found a discrepancy. It seemed like on short length scales, very short, I mean, just a few centimeters. We're not talking the solar system where we know that Newton's law of gravity works. We're talking on centimeters. It seemed like Newton's law of gravity didn't quite work. And if that result is right, then that would be a guaranteed Nobel Prize. And they spent months checking this and checking that, and they could not figure out what was wrong. And then finally, someone said, hey, you know, we have this translation stage, just a mechanical device that moves something to a fixed position. You can just dial in the distance you want and it moves it there. We never calibrated the translation stage. And they said, oh, but the manufacturer said it's good to whatever level of precision. And they said, yeah, but we didn't check it ourselves. And so they checked the translation stage. And sure enough, the manufacturer, a company that I will not name because I have some friends who work there, the manufacturer had screwed up. And they sent them a very nasty note. But they really thought for a while that they might have a Nobel Prize coming because there was this discrepancy, and it was all because these distances were just systematically off by a few centimeters, which is just completely breaking the data. And that is why we do basic calibrations on Zmax. Not that I think Zmax will fail these calibrations, but because that's how we do science. Are there any questions on the project at this point? Okay, well, we've been going for a while. Let's take a 7-minute break and come back at 6:10, and then we'll just do some ray tracing examples. So get up, stretch your legs, get a drink of water, whatever. Okay, we'll get started in a minute. Oh, I was going to tell you, so last week I got to see some physics in action. Every now and then I have to get an ultrasound of the heart because there's certain things in the family history. And that is so cool. I mean, it's not exactly pleasant knowing that there are certain things in the family history, but it is so cool to be, because what happens is you're lying on this bed and they're just running the ultrasound wand over your chest. And sometimes they ask you to inhale or exhale or hold your breath or whatever. And you're looking at the screen as you're lying there, and you can see the heart valves flapping open and shut. And it is so cool to just watch the valves of the heart flapping open and shut. And they can measure the velocity of the blood flow from the Doppler effect. And so you're looking at this image of your heart with color-coded velocity profiles. You can actually see inside the chambers. And if the blood is moving fast, it's one color. And if it's moving slow, it's another color. And so you can see a velocity profile of the blood inside a chamber of your heart. And that is just such cool physics, to think that this is like a completely ordinary thing that like any neighborhood clinic will have, that they can just look inside your heart and do an ultrasound and measure the blood flow and actually watch the valve open and shut while they got a bunch of electrodes measuring the electrical activity. And so it's like a movie where you see that, all right, when the electrical activity rises, here's where the valve is. When the electrical activity falls, here's where the valve is. It's just the coolest freaking physics to think that these things are possible, that once upon a time would have been considered magic. The reason that came to me is that while I was on break, I got a voicemail from my doctor. I'm like, oh, I should tell them about that. It is just really cool. All right. So I want to go over a few more things with ray tracing. One thing I want to talk about is depth of field. We were doing that through focus spot diagram, where we could see what would happen if you move the focus a little bit. Would things change very much? Depth of field is sort of the opposite of that. Instead of moving the image plane and seeing if I move the image plane, does the focus change very much? This is what happens when you move the object. So I've got a lens and I'm going to draw an object. I always do traditionally a Christmas tree. All right, and we'll decorate the Christmas tree. And a few more. Yeah, the gold doesn't show up very much. Anyway, so first we're going to look at this. Oh, and I need to indicate the focal points. So I'll put focal points here, a little bit past 2.5. So a little bit past 1, past there. So I'll put focal point there and there. So, all right, we start with this, oops. We start with this bulb. We do our ray tracing, and our first ray goes through the focal point. And what's it going to do once it gets to the lens?
It's going to go straight.
Parallel to the optic axis. And then we take another ray parallel to the optic axis, and that ray is going to go through the focal point. And if I did all of this to scale, which I more or less did, then the ray that goes through the center of the lens will meet up there as well. Now, we could also ask about this bulb right here, which is closer to the lens. And we could trace rays from that bulb. So we would again trace one through the focal point, and it's going to go parallel to the axis when it comes out. And there will be one that goes parallel to the axis, and it will go through the focal point. And then finally, there's one that goes through the center. And this is pretty far. This Christmas tree is pretty far from the lens. And so 2 points on it, 2 things to notice. First of all, because it's pretty far from the lens, the image is squished. All right, the image, the first bulb was 1, 2, 3 squares up, and now it's like basically 1 square down. So the images got compressed by like 1/3, all right? Because it's more than 2 focal lengths away from the lens, the image has gotten shrunk. And furthermore, yes, technically the blue rays came to a focus at a slightly different distance, but we'll never be able to tell from this diagram. And not just because I drew poorly, but because the distances that we're talking about here are really small. So we could say that in this case, we have a wide or deep depth of field, meaning that we can have things that are at 2 different distances from the lens, and they're both almost perfectly in focus in roughly the same plane. Two objects from different distances are both approximately focused. You know, we can argue over whether or not where exactly to put the lens, but it's kind of like the thing in Zmax where you do the quick focus and it's compromising between the 2 objects. You're trying to decide which one to focus on. They're both so close, it's not going to matter much. On the other hand, if we did something like this, let me try it like that. All right, now once again, I will put the lens, will say that the center is there. And so I'll put a focal point here, a focal point there, and I'll put a focal point there. Now I'm going to put an object much closer to the lens. I'm going to put a ball over here. All right, and this ball is much closer, so we're going to look at a point on the top of the ball, and that ray still goes parallel to the axis, and because it went parallel to the axis, it goes through the focal point, and this other ray goes through the focal point. And then I did everything correctly, more or less. That gets focused. Now I'm going to do it in a different color just so we can tell things apart. I'm going to look at a point here, okay? And the first ray goes parallel to the axis and then goes through the focal point. And the second ray goes through the focal point and it goes up to there. And the third ray goes like that. And what you should definitely be able to see is that these 2 points are not at all in focus. Can anybody think of an explanation for that beyond the fact that, well, we look at the rays and we see what's going on? These 2 points have different S1 values, right? They're at different distances from the lens. And the derivative of S2 with respect to S1 is big when S1 is approaching F. And these are pretty close to the focal point. They're both close to F. All right, different distances from the focal point, but both fairly close to it. I mean, certainly closer than the first case there. And so if we look at this graph of S2 versus S1, over here it has a very steep derivative, okay? So when you're doing this close-up, S2 changes rapidly if you just change S1 by a little bit. Whereas up here, small delta S1, small delta S2. As a matter of fact, not just small, even smaller. Any questions on that? One thing you could think of is when you play with a cell phone camera, there's a reason why cell phone cameras work fairly well for taking pictures of things that are many focal lengths away. Anybody want to guess roughly what the focal length in a cell phone camera probably is?
About 4 millimeter.
Yeah, if that much. I mean, these things are really thin, right? So definitely less than a centimeter, probably, I don't know, it's hard to tell for sure. Probably depends on the camera, but definitely at best a few millimeters because they're so thin. The distance from the lens to the image plane can't be that large. And so anything that's more than a few centimeters away is going to be really far away. On the other hand, if you try to do some extreme close-up, you could eventually run into a problem. I mean, if I did like a sufficiently extreme close-up with this thing, but again, that focal length, you can't see my laptop, but the screen, the camera is embedded in a very, very thin screen. So again, it's probably just a few centimeters. So I'm putting my finger up to it. I have to put my finger pretty close before the surface gets blurry. Even back here, you can see striations on the surface of my finger. All right, I have to really put it close before it gets blurry. No questions on that? All right, we've been talking about what happens when we get close to the focal point. Now let's get closer than the focal point. So for the focal point, that was 1, 2, 3, 4, 5, 6 away. So 1, 2, 3, 4, 5, 6 away. All right, and we've got an object right here. So our object is closer than 1 focal length. A ray going parallel to the optic axis still goes through the focal point on the other side. The lens has no way of knowing that it didn't, well, it did go through the focal point, so it doesn't matter. And a ray going through the center still goes unperturbed on the other side. But a ray that seems like it came from the focal point, the lens sure thinks that it came from the focal point. It's traveling as though it came from the focal point. It has no way of knowing that it didn't actually pass through the focal point. So it just sends it parallel to the optic axis. Now, it's sure these rays are never going to come together, all right? But that doesn't mean that they don't form an image of some sort. They do form an image. It's not an image that you can focus onto a piece of paper, but if we look through the lens on this side, if we're over here with our eye, and I do a terrible job of drawing an eye, if we're over here, there's a person over here looking through the lens, we sure see an image. But the image we see, the rays of light that are coming to us, they don't look like they're coming from where the object actually is, right here that I'm Xing. It looks like the rays are coming from up there, right? This is called a virtual image. It's not the sort of image where you could put something there and receive rays of light. It's not like in all of the cases that we were doing before where I could actually put something where this blue image is forming, or put something where this red image is forming, and rays of light will be received there. I could put a detector there, and light will come in, and chemical reactions will happen, or electrons will gain energy and send signals through a circuit. But that's not what's going to happen here. What's going to happen here is that we can't actually put something where the image is, but the rays of light will behave as though they're coming from there. So like a magnifying glass would be a perfect example of that. You hold a magnifying glass up to something and it looks bigger. This is why. Now, have you ever noticed that with the magnifying glass, if you hold the magnifying glass at the right distance, it looks big and right side up. But if you pull the magnifying glass away, it looks upside down. Can anybody guess why the object would look upside down if the magnifying glass is too far away from it? No guesses?
I'm trying to think. So this is if the magnifying glass is pulled back, right?
Mm-hmm.
So then the object, I guess, would be at a distance considerably larger than its focal length.
Yep. So let's say the focal point is here, and then we've got another focal point there, and we've got an object, got, say, a person. We're looking at a person across the room through that lens, why does the person look upside down through the magnifying glass? Let's just trace the rays of light and see. So let's start with the rays of light from the hand.
Well, is it because the rays that go through the center of the lens don't change direction? So rays from the top get focused at the bottom, and then rays at the bottom of his feet get focused at the top.
Basically, but I want to go a little bit further with it than that. As far as someone on the right side is concerned, it looks like the person's hand is right there, right? There are rays of light spreading out from there. Now, obviously, for mechanical purposes, for a lot of physical purposes, well, light is a physical thing, but for a lot of physical purposes, there is no person there. There's nothing solid or substantial there. But rays of light are coming from there. For optical experiments, it sure seems like there is a hand right there. And likewise, it seems as though there is a foot. Well, let's just find the position of that foot. It sure looks like there is a foot right there. For any optical purpose, there is a hand here, and there is a foot there. That's the physical idea of it. That's the geometrical idea. Let's talk about the math of it. We know that S2 is equal to S1F over S1 minus F. All right? Now let's say that S1 is less than F. Well, then this is negative. S2 is less than 0 if you put the object closer than one focal length away. And all that means is that it forms on the opposite side of the lens that you were expecting. So if we've got an object up here, less than one focal length away, the image forms there. S1 less than F, S2 less than 0. This should also help explain something that happened in Zmax. When you were doing the first project and you did a quick focus and you got a negative distance, a negative layer thickness, that just means that Zmax was extrapolating rays backward. So let's go back to the lens that we were working with a little while ago. And we set this thing up so that the focal length was roughly 10. Zmax is saying that the effective focal length is 10.38. And the reason why it's not exactly 10 is, one, I didn't calculate the refractive index perfectly, and two, I didn't take the thickness of the lens into account. We'll get to the thickness of the lens in a few weeks. But let's just see what happens if we make this layer thickness less than the focal length. All right, well, if we go to the spot diagram, sorry, not the spot diagram, the layout, it looks like the rays are spreading out. It's not necessarily clear where the rays are spreading out from. So let's just do a quick focus. If we do a quick focus, it looks like they are spreading out from points back here. And that's really, really ugly because it's a pretty terrible focus. So how could we get to visualize what the rays are doing on the right side?
Don't you go to settings and then change the last layer that's drawn?
Change the what?
The layer that where it finishes drawing.
Yeah, but what if I want to see, what if I do want to see this backwards extrapolation, but I also want to see the off-axis, but I want to see the backwards extrapolation, but I also want to see what's happening on the right. And by the way, let's make the aperture smaller, because if we make the aperture smaller, then we get much less of this ugliness. Small apertures give good images. I want to see the rays travel a little ways on the right before they extrapolate back.
You should add another layer, right? Like how we did in the homework.
Exactly.
Yeah, okay. Yeah.
So I'm going to insert another surface. So I'm going to make one of these layers, say a thickness of 5, and then 5 plus the negative 11. And that's not quite right. So here's what happens. The rays are traveling, they hit the lens, they go through the lens, they spread out. If we extrapolate back how they spread out, it looks like they came from over here. Likewise, the green rays are traveling, they hit the lens, they spread out. If you extrapolate how they spread out, it looks like they came from there. That's what virtual images are all about. Any questions? You guys are very quiet. Nobody has any questions on any of this.
I'll ask a question.
Sure.
So this virtual image, we can't particularly measure in any way experimentally. Is there an experiment where you would measure the rays to the right of your diagram that are actually there in order for you to figure out where your virtual image is?
So certainly you could do some measurements of the rays on the right side of the diagram and extrapolate backward. Another thing you could do is you could be viewing on the right side. You could be standing on the right side. And you could have someone put an object where it looks like the rays are coming from on the left side. And then you could move your head. And you know that if you move your head and look at something from different angles, it moves, right? If you move your head, then something that was in your, if you move your head, something that was originally in the center of your field of view goes to the side, okay? And you could basically see, while the object that someone's holding on to doesn't move in your field of view in the same way that the virtual image moves. Because if they both look like, if the light from them is behaving as though they come from the same distance away, from the same position, then when you move your head, its apparent position should change in the same way. Okay? If it really is here, or if the light really is behaving like it's coming from there, then when I look at it a little bit differently, it should change in my field of view in the exact same way that, you know, an actual tangible object at that point would change. That's called a parallax measurement. So people will do that and look at it from different perspectives and verify that, yeah, it shifts in the same way as something positioned there would shift.
So virtual image undergoes parallax as well.
Yep. Let's talk about lenses that are explicitly designed for virtual images. Let's talk about concave lenses now. We've been doing lenses that are convex, they bulge outward. There are also concave lenses. Sometimes the lenses are bulge inward a lot on one side and bulge outward just a little bit on the other side. This would be like glasses. And the idea of a concave lens is quite simple. It's just the opposite of a convex lens. So it goes with all of the opposite rules of what you learned for convex lenses. We learned that for convex lenses, if we have a ray going parallel to the optic axis, it goes through the focal point. Well, for these lenses, it's the exact opposite. It goes as though it's traveling away from the focal point. A ray going through the center of the lens still doesn't change direction. All right, that ray still continues on because it's hitting what looks like a purely vertical flat surface. And as long as it's thin, it goes on. And then here's the part that's going to seem a little bit weird. If we had aimed, let's see here, that's 1, 2, 3, 1, 2, 3. If we had aimed a ray at the focal point, what that ray will do instead is it will go parallel to the optic axis. Because it's going parallel to the optic axis, it will look like it's coming from there. And so these lenses behave, these lenses still form images. They form virtual images. The center ray obeys the same rules, but everything else is reversed with the focal points. A ray going parallel to the optic axis goes away from the left focal point instead of going towards the right focal point. And the ray aimed at the right focal point instead of the left focal point goes parallel to the optic axis. Any questions so far?
So if you say instead you come in at a certain angle, so then it would go parallel to the optic axis. Is it at any angle it goes parallel to the optic axis?
Oh, if I wanted it to go parallel to the optic axis, I would have to aim a bunch of rays at the right focal point. So if I had a bunch of rays aimed as though they were going to there. So to aim it there, but then I'm going to pull it back to there, and then I'll aim it there, and I'll pull it back to there. Those rays will do this. So one thing you could do is you could take focused light and recollimate it.
Mm-hmm.
So imagine that we had, say, another lens here. All right, say I had another lens here. I could take that other lens and I send in a bunch of parallel rays. and I set up all these parallel rays, aiming them at there, aiming them at there, should be doing it like this, then they will all go like that one. They will all go parallel to the axis. So this would be a way to collimate a beam. And if I ran it in reverse, this would be a way to expand the beam. It's not the only way that I could do it. Technically, I could also do that with two rays, with two lenses like this, but they would have to be farther apart, as you will see.
Betsy asked if we could consider concave lenses as like a divergent.
Yes, diverging lens is another word for them. Sorry, I wasn't looking at the chat, so thank you for bringing that up. These would be considered diverging lenses. So what I was gonna show is that you could also do this. One thing you could do to collimate a beam is this, right? So you tell me, what would this first distance, oops, what would this first distance be? What would this be?
The focal length of the first lens.
Yep, this would be the focal length of the second lens. You could do that. But now here's the beauty. If I did it this way, I know that I didn't draw these so that the focal length is the same in both cases, so just humor me. But in this case, we're aiming at the focal point of the first lens. And we aim at that, but then we put the second lens one focal length away. Really, this should be minus f2. So which of these setups would you rather use to collimate a beam?
The second one?
You'd rather use the second one? Why?
So in the first one, you're aiming the beams from the first lens at the focal point of the second lens, right?
Yep.
So if you move the second ones, like it makes it more fragile, right? Because if you move the second ones, then don't you have to change like the distance between them, or?
Well, either way, I need to have.
Like, I want to have the most stable setup, basically. Like, I want the one that allows some allowability of play.
Well, the reality is that either of them only have so much play. Which one's going to take up more space?
The second one.
Second one, yeah. So in both of them, you need to have that the separation is the sum of the focal lengths. Here you're taking a positive focal length plus a positive focal length. Here you're taking a positive focal length plus a negative focal length.
Okay, I see. I see why the setup would be much smaller.
You
You put them like really close then, like almost touching?
Well, that would all depend on what kind of compression you're aiming for. If I want to get really, really good compression, I want that second lens to be almost at the focal point. If I want only modest compression, I could put that second lens much farther from the focal point. There was another question.
Oh yeah. So I'm kind of confused on your first setup. your f1 is the focal length of that first lens on the left, correct?
Yep.
Now, I thought that that point that it's going to, that's technically the point of the focal point of your second lens.
It is.
Okay, so you're setting those two equal to each other.
Yeah, I'm having them line up, just like I'm doing here. Here, the focal point of the first lens is also the focal point of the second lens.
Okay. Yeah, that makes sense.
Okay, it's 6:50. I'm not going to keep you any longer. Next week, we're going to talk about another case where we use these concave lenses. Spoiler alert, many of you are wearing them right now. We're going to talk about how the eye works and why we use concave lenses in eyeglasses. So have a good weekend, and I'll stick around for a few minutes if people have any questions.
When considering how to correct for aberrations when adding lenses to a system and that kind of stuff, are both types of lenses typically used, or is one preferred over the other?
Oftentimes they use negative lenses. They use a combination of positive and negative lenses. Look up the Cook triplet. The Cook triplet is a famous lens design that uses both.
Okay, thank you.
Keith, Corey, you have any questions?
No, I'm just taking up the notes.
Okay, I'll also post these notes online in a few minutes, so, but you can take your time.
I think I just finished up right now, actually. Thank you.
Okay. Keith, do you need anything? All right, Keith, well, if you don't have any questions, I'm gonna sign off and you can always come to office hours. Bye.